Okay, so now that we know what critical points are and we know how to find them, we can start to specify which type of critical point it is that we've just found, okay, without needing a graph. So, there are three types of critical points. We have our minimum, our maximum, and our horizontal point of inflection. Okay, so the minimum I like to think of being at the bottom of a bowl, and the maximum's like being at the top of a hill, okay, and the horizontal point of inflection is that little kink in the middle there. Okay, but these aren't very mathematically correct ways of explaining what a minimum, a maximum, and a horizontal point of inflection actually are. Okay, bottom of a bowl isn't very mathematically correct. So how can we make it mathematically correct? Well, if we start off with our minimum, okay, we can see that if we start when say x is equal to -1, here x is 0, and then over here x is 1. Okay, so we start at the left-hand side. So over time, we see a negative gradient, okay, negative gradient, all the way until our gradient is equal to 0. Okay, there's no gradient, or the gradient is equal to 0 at the critical point there, and then the gradient starts increasing again as we move out the other side. Okay, so we have a negative gradient, 0, positive gradient. And if we do that for all three, so for the maximum, we can see that here we have a positive gradient coming up until we get to our critical point where the gradient is 0. And then we come back down the other side and our gradient starts being negative again. So over here we have a positive gradient to start with, 0, and then negative over on the right-hand side. And for the horizontal point of inflection, we see that the gradient here is positive. It's climbing, it's climbing, it's climbing, and then it gets to 0, and then it starts climbing again. Okay, so it's positive on both the left-hand side and the right-hand side of our critical point. So it's positive on the left-hand side, and it's positive on the right-hand side. So what we can do is when we want to work out what type of critical point it is that we have, okay, we find our critical point. So we find our critical point, for example, in this maximum one here, our critical point is there. Okay, and then we want to find out what the gradient is either side of our critical point. So for example, if I draw up a little table, okay, and we say we have our critical point here, and then we have the gradient just to the right of our critical point, and we have the gradient to the left of our critical point. Okay, so our critical point is just going to be sort of like our orange dot here, and we have three critical points. Now, if the gradient to the left of the critical point is positive, and then the gradient to the right of the critical point is negative, then what type of critical point do we have? Well, to the left, we're positive, and to the right, we're negative. It's going to be the maximum, right? We're climbing up the left-hand side, and we're decreasing down the right-hand side. So we're going over a hill, okay? So that there is going to be a maximum. Okay, what about if we're negative to the left, and then we're positive to the right? That implies that we're coming down the bowl to our critical point, and then climbing the bowl back up the other side. That's going to be a minimum, okay? So we have a minimum here. And then what if we're positive on both sides? So that means we're climbing positively, and then positively again. That's going to be a horizontal point of inflection, okay? Because we just keep going. We sort of stop for a second at our critical point, and then we keep climbing again. So that's going to be a horizontal point of inflection. But there's one more, which is when it's negative on both sides. So it's negative to the left, and it's negative to the right. And we'll put our critical point here in orange. Well, what will that look like graphically? That's going to look something like this. We're going to be coming down, 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 down. Okay? We're going to get to our critical point there in orange. And we're going to go back down again. That's a horizontal point of inflection as well. It's just reverse. So if we do our gradient lines in pink, we're coming negative gradient, negative gradient, negative gradient, and we stop at our critical point, and then we come down the other side, still going down. So that one there is also a horizontal point of inflection. So we can use this table to find out, when we find our critical point, to find out what type of critical point it is. So for example, we'll come down here, and I'm going to plot the function f of x is equal to x cubed on top of 3, take x plus 3, okay? And we'll plot that on a Cartesian plane over here, right? So make this our xy Cartesian plane. Oh, come down here. There we go. Sorry about that. Have our xy Cartesian plane, like so. And what this function's going to look like, okay, I'll draw the function in red. Okay, the function sort of, it comes down from here, and it comes up, across, and something like that, okay? Roughly something like that. And what we notice here is we're going to have two critical points here, okay? We have a critical point here, and the gradient is 0, and we have a critical point here, where the gradient is 0, okay? And the first critical point appears to be a maximum, okay? That one there appears to be a maximum, and the second one appears to be a minimum. But what if you didn't have this graph and there was no way of finding or being able to sketch this graph, okay? And you had to find out what types of critical points they were, just algebraically. So if we find the critical points, remember the critical points are when the gradient is equal to 0. So what is the derivative of f of x? Well, that is equal to 3x squared on top of 3, take away 1, okay? And we can simplify that down to x squared minus 1. And we want to know when that is equal to 0, okay? So we're going to solve this part. Well, x squared is equal to 1 if we add 1 to both sides, which means x can be plus or minus 1, okay? So what are the two coordinates for our critical points? Well, we substitute when x is 1 and minus 1 back into our original equation. So when x is 1, so f of 1 is going to be equal to 1 cubed on top of 3, which is a third, take away 1 plus 3. And that is, or a third take away 1 is going to be minus 2 thirds plus 3. So minus 2 over 3 plus 3, which is going to be 2 and 1/3, okay? Or we can we'll write it as 2 and 1/3, or we can write that as 7 over 3, okay? So that is what f of 1 is equal to, and then what is f of minus 1 equal to? So we'll do that over here. F of minus 1 is going to be 3 lots of minus 1 cubed, okay? Back up to this equation again here. So minus 1 cubed is going to be minus 1. So we're going to end up with negative a third. And we're going to be plussing 1 this time, adding 3. So that is negative a third plus 4, which is 3 and 2/3, which we can rewrite that as 11 over 3. Okay, so we have 2 points there. We have the point 1, 7 over 3, and the point minus 1, 11 over 3. So there are 2 points, but we want to know what types of critical points these are. So if we start off with the first one, 1, 7 over 3, okay, and we can see that that is going to be our minimum off of our graph, okay, but we want to confirm that. So what we're going to do is we're going to take 2 points either side of our critical point. So for example, on the graph, it's going to be taking a point just here and just here and seeing what the gradients are at that particular point. So remembering that the derivative of f of x is equal to x squared take 1. Okay, so the derivative of f of x is equal to x squared take 1. And we want to know what the derivative is at the point 1. Well, we know it's the derivative is going to be 0 at that point. So this is x. If we draw up a table, x, and then the derivative of x, so at 1 it's going to be 0. We found that. And then say at 0.99, and then at 1.01. Okay, and we're going to put these into our calculator. So 0.99 into this equation and 1.01 into this equation. And that will tell us what the gradient is at that particular point. So if we put that into our calculator, we're going to get 0.99 squared. And then we've got to take 1 off it. And we end up with, if we write it as a decimal, negative 0.0199. Okay, but the important part is that this is negative. And then 1.01, so we do 1.01 squared, take away 1. We end up with 0.0201, and that there is positive. So we can see that if we take the point at 1, okay, so on our graph it's the minimum, we can see that just to the left, the gradient is negative, which means it's coming down. And just to the right, it's coming up. So if on the left it's negative and on the right it's positive, we can come over to this table here. On the left it's negative and on the right it's positive. It's going to be this one here. Okay, it's going to be a minimum. So we can say at our table that the point 1,7/3 is a minimum. Okay, but what about the next point here? Okay, when x is negative 1. So remembering again that the derivative of x is equal to x squared minus 1. That's going to tell us what the gradient is at any point. And we want to know what the gradient is when x is equal to just either side of minus 1. So we might pick minus 1.1 and minus 0.9. Yeah, minus 0.9. Okay, and we want to know what the derivative is at these points. So we know what x is, and we want to find what the derivative is. Well, we know that at negative 1, the derivative is going to be 0, okay, because it's a critical point. But if we put minus 1.1 into our equation, so minus 1.1 squared, take away 1, that there is going to give us 0.21, and that is positive, okay? But what about negative 0.9? So if we do negative 0.9 squared, take away 1, we end up with minus 0.19, and that there is negative. So we can see that we're going positive gradient, positive gradient, positive gradient, positive gradient up to our critical point, and then we've got negative gradient, negative gradient, negative gradient, negative gradient, negative gradient on the way back down. And this forms a nice dome, which is like going to the top of a hill, which we know is a maximum. So we can say that the point minus 1, 11/3 is a maximum. Okay, and we can confirm that at our graph, okay, because we see here the point 1,7/3 and the point minus 1, 11/3, they're correct. Okay, we've got the maximum and the minimum correct. Okay, so that's how we use what we call the sign test, which is down here, using this negative and positive, called the sign test, to work out if we have a minimum, a maximum, or a horizontal point of inflection. Okay, the last one that we want to do, we'll have a go at doing a horizontal point of inflection question. So we'll come down over here somewhere, and we're going to say that this time f of x is equal to x to the power of 5 plus 2. Okay, and we want to graph this on a Cartesian plane. So we'll bring up our Cartesian plane like this. XY, Cartesian plane, and I'm going to graph this function in the red, and it's going to look something like, it's going to come up here, it's going to have a little kink in there, and it's going to come out the other side. Okay, so we can see off the graph that the critical point is right there. That's when the gradient is equal to 0. And if we have the graph, we can see that it's a horizontal point of inflection. Okay, but we want to prove this algebraically. So what we can do is we can find, well, what is that critical point in orange? We know that that is when the gradient is equal to 0. Okay, so the derivative of x is equal to 5x to the power of 4 plus 2. Okay, and we want to find when that is equal to 0. So we solve that. We say that 5x to the power of 4 is equal to minus 2. We divide both sides by 5. X to the power of 4 is equal to... Oh, my bad, I made a boo-boo. The derivative of x, we don't add the 2 there, do we? It's just 5x to the power of 4. And we want to know when that is equal to 0, right? This plus 2 just becomes a 0 when we do the derivative. So if we divide both sides by 5, we get x to the power of 4 is equal to 0, which means x is equal to 0. Okay, and that makes more sense. So when x is equal to 0, so this is our x-axis, we have 0 here, we have our critical point. Okay, that makes sense. So the derivative of x is equal to 0 when x is equal to 0. But what is a gradient just either side of our x, either side of our critical point? So let's say here and here, for example. What are the gradients there? Well, we come up with our little table, x, and then the derivative of x. And we want to pick a point either side of 0. So we have our 0 here. We know that when x is 0, our gradient is 0. That's no problem. But what about when x is 0.1 or minus 0.1? Okay, when x is minus 0.1, we go to our gradient, which is this part here, 5x to the power of 4. So we do minus 0.1 to the power of 4, and we times it by 5. And we get a positive number. Okay, if you do that in your calculator, you're going to get a very small number, but it's going to be positive. Okay, it's 5 times 10 to the minus 4. Okay, so very, very, very small, but it's positive. And if you do the same for 0.1, okay, you're actually going to get the exact same number, and that's going to be positive as well. Okay, so that means that we are going up, 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 to when the gradient is 0, and then coming back up the other side again. And we have our critical point in here, forming a horizontal point of inflection, which looks the exact same as the graph that we have. Okay, so we can say that, or when x is 0, f of x is equal to 0 to the power of 5 plus 2, which is 2. So the point 0, 2 is a horizontal point of inflection. Okay, so that's it. So we know our 3 types of critical points, and we can now find them algebraically. Okay, I drew the little dotted lines here and here. Okay, the same goes down here, that we have a negative gradient on the left-hand side. So we're coming down, 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 down to our critical point, and then we're coming positive up the other side. Positive, 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 positive. Okay, that forms our minimum. All right, thank you.